So hello guys and welcome to my channels. Today again I am back with important numericals on machine designs. And here we can see the numericals on the screen. And here this numerical was once asked in 2019 fall. And the thermal resistivity of a stack of lamination measured along with the lamination is 0.02 ohm meters. The thermal resistivity of a stack of lamination measured along with the lamination is 0.02 ohm meter given. And the iron loss is given as here 40 kilowatt per meter cube. Calculate the value of temperature difference between the hot spot and the outside surface for the following cases. And here the length of a stack measured along the lamination is 0.2 meters and the length of a stack measured across the lamination is 0.1 meters given, and the thermal resistivity across the lamination is 40 times along the laminations. So starting the solutions, considering the total heat flow along the laminations. So first along the laminations here we have considered, so temperature difference theta is equal to q into rho I into y square upon 2. So in place of q here we have 40 and here we have iron loss given as 40 kilowatt per meter cube. So 40 kilowatt is given, so 40 into 10 power 3 in watt into, and value of rho I is 0.02 into, and in place of y we'll use here 0.2 upon 2 to the power 2 upon 2 and it will be 4 degrees Celsius. And considering the heat flow across the lamination, so for across the lamination theta is equal to q into rho x into x square upon 2. So 40 into 10 power 3 into rho x, and here you can see the thermal resistivity across the lamination. For across the laminations it is 40 times along the lamination, so 40 times along the laminations, so 40 into 0.02 into, and right now the value of x will be 0.1 upon 2 square, since the length of a stack across the lamination 0.1, and we will take 0.1 upon 2, so we will get 40 degrees Celsius here. So the temperature difference across the lamination is 40 degrees Celsius. Similarly along the lamination is here 4 degrees Celsius. And now here we have the next one. The copper loss in a winding 25 mm thick radially is 20 watt per kg. Here the copper loss is given as 20 watt per kg radially, and the thermal resistivity of a paper insulation used in the coil is 8 ohm meters, and the copper the copper space factor is 0.7. and also here the thermal resistivity of paper insulation in the coil is 8 ohm meters, and the coil is mounted on a form of infinite thermal resistivity, and calculate the maximum temperature difference between the coil surface and the windings, and 1 cubic meter of copper weighs 8900 kg. So here we have to calculate the maximum temperature difference between the coil surface and the windings. So here the maximum temperature difference between the coil surface and the winding is given as theta is equals to q rho e into t square upon 2, and in order to calculate the value of rho e we have rho I into 1 minus sf to the power 1 by 2, and rho I is given as 8. Here you can see the thermal resistivity of paper insulation is given as 8 ohm meters, and also the space factor is given as 0.7 where. So rho I into 1 minus space factor is space factor to the power 1 by 2, so 0.7 into 0.7 to the power 0.5 will get 1.31 ohm meters. So and q will be here, the value of q is given as here, the copper loss is given 20 watt per kg, and the space factor is given as 0.7. Similarly 1 cubic meter of copper weighs 8900 kg. So q is equals to 0.7 into 20 into 8900, so it is going to give in watt per meter cube. So it will be 124600, and now finally the theta will be, we'll just substitute the values here, q rho into t square, we have written the q rho e and t, and if you substitute all the values you will get the value of theta. So The maximum temperature difference will be here 51 degree Celsius. And now here we have the next one. Calculate the temperature difference between the center of the embedded portion of the conductors and the overhang, and the length of the machine is 0.5 and the current density in the conductor is 4 ampere per mm square, and the thermal resistivity of copper is 0.025 ohm meters. Assume that the total heat produced in the conducted along the length of conductor, and the electrical resistivity of conductor is given as here 0.021 into 10 power minus 6 ohm meters. And here this numerical was asked in 2016, either it was asked in fall or springs, I did not remember it was, but it was asked in 2016. So here in these questions all the parameters are given the question, just you need to remember the formula and apply this. So theta will be rho del square rho c L square upon 8. So here the value of rho is also given. Here you can see the electrical resistivity of conductor is 0.02 into 10 minus given. Similarly the value of del is also given, means the current density is given as here. You can see the current density in the conductor is 4 ampere per mm square. So 4 into 10 power 6 square into rho c, and here the rho c value of rho c is given as 0.025. Here you can the thermal resistivity of copper is given 0.025 ohm meters into L square, and the value of L is given as here. The length of machine is 0.5 and so L square upon 8, and it is going to give 26.3 degree. So this was all for today. Hope you enjoyed the lecture. Thanks for watching, and please don't forget to subscribe to my channel, and also don't forget to share my channels to your friends. Thank you.